Today I'm going to give a very high-level intuitive introduction of graph neural networks. And what I mean by graph neural networks is basically we want to do deep learning on data sets that can be modeled as graphs. So a little bit of intro on deep learning. So if you are doing any sort of supervised learning, you have your inputs and your associated labels Y. In traditional machine learning, you learn some sort of a function that basically captures the relationship between your input and the output. The basic idea behind deep learning is that we stack a bunch of functions. And the reason we do that is that in the end, we end up learning a much more complicated function that can effectively, if your data set has enough samples and complexity, then this complex function can learn the relationships in the data set really well and make way more accurate prediction. And that's the reason why deep learning models are so powerful. So how do we do deep learning for graphs? Well, let's first define our graph. It's a general language for describing entities with relationships or interactions. So we call these entities nodes. And if two entities are interacting or have a relationship, we define an edge between our nodes. So it turns out that majority of the real-world data sets can be described as graphs. So you can think of a social network, you can think of a disease pathway, connections of neurons in your brains, knowledge graphs. There have been some really nice talks about that here at CGSI. Regulatory networks, molecules, and even 3D shapes can be described using a graph. And so if so many data sets can be modeled as graph and deep learning is really nice, then the idea is that we want to build deep learning models that can explicitly model these relationships in the data sets because that will lead us to better performance. So until GNNs were introduced, what was happening? It turns out that the existing deep learning models were working really well, but they were mostly designed for grids and sequences. So when I say grids, I'm talking about an image, which is a grid of pixels. And convolutional neural networks work really well because what convolution does, it aggregates the informations of neighborhood pixels, learns these very nice local patterns and relationships, summarizes all that information, and makes very accurate prediction about what that image should be. In terms of text and speech, we have recurrent neural networks. I know nobody uses them anymore, but they were the original sequence modeling techniques. But even transformers, for that matter, can basically very nicely model the sequential dependency that exists in the data set. So the idea here is now, why was it difficult to build neural networks for graphs? Well, let's talk about first what these neural networks are doing. They are summarizing information. How do the existing methods summarize information? Well, in case of grids, the CNNs basically pass information from the neighboring pixels. In sequences, you basically pass the information along the sequences. So even in transformers, the role of positional encodings that you apply to your input is to let the transformer know that there is a sequential dependency between the words, because without that, you will miss out on that structural information. So that's how the existing networks summarize information. And then in both the cases, there is an obvious direction, an obvious way to direct this computation towards a single point. In case of a grid, you are directing information towards the center of the grid, so the center pixel. And then in the case of sequences, you are directing information towards the end of the sequence. So these data structures are easier to deal with. Networks, on the other hand, are complex. So they can be of arbitrary size. They can have complex topological structure. So unlike images, your graph won't have this very nice spatial locality that you see in the grids. And there is no fixed node ordering. Different graphs can be ordered in different ways. And there is no reference point. There is no endpoint. So this structure is much more difficult to deal with than your regular grid and sequences. So then the question becomes, how do we summarize data sets, or how do we summarize information along the nodes of the graph? So let's take a slightly different view of summarization. What's happening with our data summarization? We are basically doing two things. First is, we are passing information along the elements of the data which have a relationship. And then we aggregate per element level information into some sort of a summarized description, some summarized representation, embedding, whatever terminology you want to use. So these are the two steps. And what we are going to do is we are basically going to use these two steps to design a graph neural network. Okay? So I have spent some time motivating the problem and telling you that it's important. And so next what I'm going to discuss is how do we do this information passing in graphs for neural networks. Then I'm going to briefly talk about how do we actually use these graph neural networks. And I'll end it up with a very nice formulation of graph neural networks called graph attention networks, which are very popular in the field. So first question is, why do we even want to pass the information? So let me throw an idea at you as how I can summarize information for the graphs, and you tell me what's wrong with it. So suppose I have a graph. Why don't I just aggregate the information about the descriptor on the node? So what do I mean by descriptor on the nodes? Some node features. So some numerical values that describe my node. For example, if I'm thinking of a social network where each person is a node, I can think of a vector which describes this node. This may have some numerical information about the age of the person, whether they're employed or not, and so on and so forth. So that's a vector. So I have my node features for all the nodes. I can just concatenate all this information and throw into my model and make predictions. What's wrong with this very naive strategy?
You're not capturing any relationships.
Exactly. I'm not capturing any relationships between my entities. So if you can imagine in transformers, if you remove positional encodings, then you are just feeding the transformer a bag of words. So it's completely doesn't know what relationship exists between the words. And that's the same problem here. We are completely ignoring the relationships that exist between the node. So this strategy may work, but it's not a very good strategy. So then the question becomes, well, we have to figure out a way to pass information along the edges. How are we going to do that? It turns out we are going to generalize an operation that we have already seen before and see how it operates on the graph. And that operation is convolution. So if you remember, for image convolution, what you are doing is to learn a representation of a pixel in an image, we take an aggregation of the pixels which is in the immediate neighborhood of that particular pixel. Another way to think about it is we are doing this sort of information passing here. We are aggregating the information of the surrounding nodes to learn the representation of the node in the center. And you can see that it has already started looking like a graph. However, unlike images, your graph won't be these nice grid structures. The graph would look more like this. But the idea basically remains the same. So how do we define convolution on this? Well, first, what are my inputs into the graph neural network? I need two sets of information. So if I have a graph that I want to feed into my GNN, I need node features, so my vectors that describe my nodes. And then I need an adjacency matrix, which is telling me what are the relationships between the nodes. So here, adjacency matrix is a square matrix, number of nodes by number of nodes. If the nodes are connected, I'm assigning a value 1, if not 0. This is a very simple binary adjacency matrix, but if you have a weighted graph, you can replace these binary values with the weights of the edges that you may have. But for now, let's keep the example simple. So that's the input into the GNN. All right? So now let's talk about how the information gets passed, and we call it message passing, which is the passing of information between the nodes of the graph. So first, everything is initialized with X, which are the original or the starting node features of the graph. We start by mapping these node features to some hidden state representation H using some neural network function that we may already be familiar with. It could be a linear operation, it could be a nonlinear operation, whatever you like. Once we have learned this representation, now we are going to basically use another neural network to compute message between two nodes of the graph if they are connected. And this is what that function would look like. So the input into this function are basically the hidden states of each node. If there is any information along the edge, we might want to include that as well. And the output is basically a new representation, which is basically the messaging being passed between nodes. So here, this particular node H1, this node with the representation H1 has 3 neighbors. So I do it for neighbor number 1, neighbor number 2, neighbor number 3. I have calculated the information that needs to pass. And then finally, I'm going to aggregate all that information to learn the new representation of that node. So now this node has taken information from its immediate neighborhood. And for aggregation, I can just use summation or concatenation. Now, the message passing scheme that I have just described is a very general scheme. And as you can see, there are different functions and different decisions you can make. And so depending on what decisions you make, you end up with different formulations of graph neural networks. So there are tons and tons of graph neural network formulations, and I'll talk a little bit about that in the end. But basically, this is the general scheme, and then based on what decisions you make about how you want to initialize your nodes, how you want to aggregate information across your nodes, can lead to different formulations. All right, so that's message passing. And then I have one more important point to make before I talk about how we use GNNs. So just like convolution, the more layers you have, the further and further information you aggregate from. So the higher your receptive field is as you add more layers. It's the same idea with graph neural networks. The more layers you add, the further and further information you aggregate from. Why is that happening? Well, if I'm the node and we did layer number 1, I have got information from my immediate neighborhood. But my neighbors also went through that same operation and got information from their neighbors. So now when I repeat this step as layer number 2, when I do this aggregation of my immediate neighborhood, I'm pulling information not only from my neighbors, but from my neighbors' neighbors. So now if I do it a third time, I'm aggregating information that is 3 hops away. And so that's the whole idea of getting information from further and further away by adding more layers. So with that, now that you know the basic message passing scheme, let me walk you through an actual formulation of GNNs. This was one of the first ones that became very popular because they could actually do this for large graphs. So they call it graph sage. And there are a lot of terms in this equation, but let me walk you through it one by one through a toy example. So I'm going to show you how we are going to calculate the embedding for this node, which I have marked as a star. So first thing first is initialization. As you can see here, they picked, basically they didn't pick any function for initialization. They just said, whatever my original node vector is, that's my initial hidden state. Fine. So that's my initialization. And for their message passing and aggregation, they are doing a very simple step, which is a weighted aggregation of all the neighboring nodes, normalized by the size of my neighborhood. Any ideas as to why we might be normalizing by the number of nodes? Exactly. Different nodes will have different number of neighbors, so we don't want information to get biased. So if a node has a lot of neighbors, we don't want that neighbor's weight to be higher just because of its size. So we are normalizing by the number of neighbors. So those are my information from the neighbors. Then they have this step where they are adding the information for that node from the previous layer. So that's like a self loop. The reason we want to add a self loop is now we don't have to do explicit update of that node because we've already included information from that node. So now the new information is previous information plus whatever new information I have aggregated. And then finally, this is a neural network. We have to have nonlinear activation. So we have that to finalize. And so that's step number 1. We learned the representations for layer 1. If I were to repeat it, I would do it again for layer 2. Keep doing it k number of times, and I end up with information aggregated from k hops away. Again, neural networks, so we have these weights. These are learnable parameters, giving the model flexibility to, if there are certain node aggregation steps that don't help with the predictions, we'll assign them less weights. If they help, the model can assign them higher weights. So everything kind of works like neural networks. Now the only thing we are doing is we are doing the convolution operation on the graph. So that's message passing and a formulation of graph. Now the question is how we'll go about using the GNN. So you have a graph, you have your node features, your adjacency matrix, you feed it through a GNN, you do one step of graph convolution, activation, regularization, dropout. If you don't know those terms, that's fine. Those are very standard deep learning layers. And so you can do a bunch of these layers. You learn the embeddings on the nodes, and then you can feed it through any downstream fully connected layer over here where I say ... and you can make predictions. So the kind of predictions you can make here is node classification, graph classification, or link prediction. So what do I mean by that? Well, let's start with graph classification. So if I have a bunch of graphs and they all have a label associated with it, I can basically take all my nodes, combine that information, and make a prediction of which category does my graph belong to. So suppose you have drug molecules, you can represent them as graphs, feed it into your neural network, learn the representation, and then the GNN can make a prediction whether that molecule is toxic or not. Node classification means you have one graph, multiple nodes, and you want to make predictions on the node to classify that node as one thing or the other. So suppose you have a citation network. So each node is a research paper. The graph has relationships between these research papers, and then what you want to do is predict for each node what was the subject area. Link prediction is you have a graph, you have some nodes. Given the information that you have in the graph, you learn the embeddings so that you're able to predict whether a link should exist between two nodes or not. Where would I use that? So if you think about social network, so suppose you are on Facebook, I guess this generation doesn't use Facebook, that's fine. But you're on some social network and you are friends and Facebook, I'll use that example, has information about your friends. Based on that information, it wants to recommend you, who could be your friend. So that's the link prediction task, basically. So how do we formulate this? So if you have your inputs, your node features, your adjacency matrix, you feed it into a graph neural network, you have learned this nice representation based on the structure and the information in the graph. So if I want to now do node prediction or node classification, I can just take this representation, feed it through some sort of a fully connected layer F, and now I can make predictions on the node. Similarly, if I want to do graph classification, I can now combine all the information through concatenation, summation, whatever way I feel like, feed it through another fully connected neural network, and now I can do graph classification on the entire graph. Any ideas on how I might go about doing link prediction? Suppose I want to predict a link between two nodes. Sorry? Some sort of a distance learning on the latent representation. Yeah, so I could basically take the representations of the two nodes that I want to learn the link between, feed it to a fully connected neural network. I could also learn a similarity score. So if the similarity between the embeddings of two nodes are high, I say, okay, there should be a link here, and if not, so on. So there are different ways you can formulate it depending on whatever task you want to solve. All right. So I'll just take a few more minutes to talk about graph attention networks because they are very popular in the field. They basically use the attention framework that you may have heard for transformers. So what are we doing so far? So far, we had this graph sage formulation that was doing this kind of neighborhood aggregation step on the nodes. And so basically, we are giving kind of equal weightage to all the nodes. All the weights and biases we are learning are learned implicitly during training. But just like transformers, we could attend to different nodes based on their relevance for the prediction that we are trying to do. So in transformers, you can basically attend to words that are more important for your task over the others through explicit weighting. And so we can do the same thing for the graph neural networks. So that brings me to graph attention networks. So here we have learned the embeddings of the nodes. And what we are going to do is assign attention weights to the edges so that the nodes that are more important for the prediction have higher attention weights and the ones that less have lower attention weights. So I don't know if you remember how attention works, but it's a very simple mechanism, very generalizable. So attention, first thing we do is given two entities. So if you have two words or representation of two words, we get an alignment score, how similar those two words are. So here we don't have words, we have node representations. We get some sort of an alignment score of how similar those two representations are. We do it for all the edges, and then we do a softmax. Softmax because everything gets scaled in such a way that the values are between 0 and 1, and all the values sum up to 1. So now you have these relative weighting. If something is more important, higher weights, higher attention weights. If something is less relevant, lower attention weights. And now we have learned these explicit attention weights. We can multiply it when we are doing our aggregation step on the graph. So now we are doing this explicit weighting instead of letting the model. So just like how in transformers, you can do this explicit weighting to give more importance to certain words over the others, the same mechanism generalizes over here where you can give more relevance to certain nodes over the others. So that's just another formulation I wanted to bring. In this paper, they showed on one data set I have here, for protein-protein interaction data, the graph attention network worked really much better than the graph SAGE formulation. And then finally, how to implement a graph neural network. As you can see, this is intuitively easy to understand, but practically difficult to implement. But luckily for you, PyTorch has a very nice framework called PyTorch Geometric. So my first PhD student, Jeremy, is still very disgruntled because on his first research project, he implemented this from scratch. Now you just call these models. Like, it's crazy how easy it is now. All right, so that's your PyTorch Geometric. They have very nice documentation, installation. The two things I want to draw your attention to is when I said that there are so many different formulations of graph, I wasn't joking. Oh, wait, sorry, you can't see my screen moving. All right. Okay, let's see. No, this doesn't work. Ish. All right, this is a hacky way to do it, but it works. Okay, PyTorch Geometric. So the thing that I wanted to draw your attention to was this cheat sheet. So when I said that there are many formulations of graph neural networks, I wasn't lying. There are these many different formulations. Some of them are very specific to the kind of graphs you might be working with. So point clouds and heterogeneous graphs that you may have. The other nice thing is they also have very nicely arranged data sets. So if you just want to learn about graph neural networks, run some test code, then you have a lot of data sets that you can just load very, very easily. So feel free to check that out. All right. Great. No, that's not what I want. Let's see. All right, fantastic. So just to recap, the existing neural networks like CNNs and RNNs do not generalize easy to graph structure. So that's why we the researchers designed the specific message passing scheme that creates information between the neighboring nodes and then aggregates it to model the relationships that exist in the graph. And then once you have these nicely aggregated representation for your nodes, you can use them for any downstream prediction task on the graph, ranging from node classification, edge classification, link prediction, and graph classification. So this was a tutorial, so I didn't talk much about the lab research, but I do want to thank my lab members, because we learn a lot about these topics from just the kind of research they do in the lab. And with that, I'll be happy to take the questions.